Hello. Welcome to your Algebra 2 lesson 9.5. For today, you're going to learn how to graph and write the equations of hyperbolas. Now, we've seen hyperbolas before in terms of rational functions, but now we're going to consider them in terms of being conic sections. The set of all points P such that the difference, remember with ellipses it was the sum, for hyperbolas it's the difference of the distance between P and two fixed points called the foci is a constant. So we've got one focus here and one focus here. They're still C units away from the center. Okay, so here's a focus, here's a focus. If we take the longer distance and then we subtract the shorter distance, for a fixed amount, we get all the points on the hyperbola. Okay? All right. The line through the foci, okay, so here's the line through the foci, intersect the hyperbola at the two vertices. Well, that's exactly like it was with ellipses. What's different, though, is that this is now called the transverse axis. It's not called the major axis because it's not necessarily bigger. Okay? It's not necessarily the bigger axis. Today, A may be bigger, B may be bigger. We don't know. Okay? Its midpoint is the hyperbola center. A hyperbola has two branches and has two asymptotes that contain the diagonals of a rectangle centered at the hyperbola center. So the rectangle is going to be centered at the center. That sounds funny, but it is. It's centered at the center. And you go out A units to a vertex, and then from the vertex you go up B units to get a corner point. Then you go back to the vertex and go down B units to get another corner point. Then you go over here to the other vertex and you go up B units, down B units, and then you complete your rectangle, and then you draw in the asymptotes. It makes it super duper easy to graph the hyperbola because you've got the vertex and then you just follow the asymptotes. You just let the hyperbola approach the asymptotes. It's beautiful. All right, so you can have a horizontal transverse axis just like that first example where your foci line up horizontally. And so you have a horizontal hyperbola and it opens, the two branches are left and right. Or you can have a vertical transverse axis where the foci line up vertically. Means your whole hyperbola is going to be vertical, and you're going to have one piece that opens up, one piece that opens down. All right. So again, these equations are going to be given to you, so don't worry about memorizing them. Worry about being able to use them. That's enough to learn. All right, so when your transverse axis is horizontal, the whole thing is horizontal, and x squared is going to be involved in the positive term, and that term will come first. You'll have x squared over a squared minus y squared over b squared equals 1. Now remember, A is not necessarily bigger than B. We know that this is a squared because it's the positive term, the term that doesn't come after the minus. The term that comes after the minus has b squared as its denominator. When this is the case, the asymptotes have an equation of y equals plus or minus b over a times x. That will come out automatically whenever you use the rectangle. One way to you'll always have this equation. It makes sense if you look here, the b is associated with y, a is associated with x, and the slope is always changing y over changing x. So the constant related to y goes on top, constant related to x goes on bottom. The vertices are always a units away from the center, this time horizontally. So your vertices are going to have the coordinates plus or minus a 0. Now, when your transverse axis is vertical, that means, your two pieces, one opens up, one opens down. So y is going to come first. So you have y squared over a squared minus x squared over b squared. Again, whichever term comes first is going to be the one that has a squared as the denominator. Whichever one comes after the minus has b squared as the denominator. And so this time the slope is plus or minus a over b. And then the whole equation is y equals plus or minus a over b times x. Vertices are still a units away from that center of 0, 0, and so they're at 0 plus or minus a. The foci lie on the transverse axis, c units away from the center, so that's just like the ellipse. What's different from the ellipse is that c squared equals a squared plus b squared. So it's going to be very important you keep in mind whether you're working with ellipses or hyperbolas, which formula you use for c squared. Okay, so we're working with hyperbolas today, so it's c squared equals a squared plus b squared. Okay, so we're going to graph 25y squared minus 4x squared equals 100. We're going to identify the vertices, the foci, and the asymptotes of the hyperbola. Just like with ellipses, first thing we got to do is get this in standard form. So we want it to equal 1, it equals 100, so we're going to divide out that 100. We're going to reduce 25y squared over 100. Then we have our minus, and we're going to reduce 4x squared over 100, and all that equals 100 over 100. So when we simplify, we get y squared over 4 minus x squared over 25. Let me fix that really quickly. That's going to drive me nuts. There we go. Sorry about that. Get back to it. So we've got y squared over 4 minus x squared over 25 equals 1. We're going to identify the vertices, foci, and asymptotes. Note that a squared equals 4 and b squared equals 25 because the y squared term comes first here. That means that this is a vertical hyperbola. You're going to have an upward opening piece and a downward opening piece. The transverse axis runs vertically. So considering the vertex is going to be a units away, a will be 2, and since it's vertical to the center, it's going to be 0 plus or minus 2. Since b squared is 25, b is 5, so that's going to be important in a minute. We do want to find the foci, so we need to know c, because the foci are going to be at 0 plus or minus c. So we're going to use our formula. So c squared equals a squared plus b squared. Let me fix that. Goodness gracious, just full of little typos. I can't believe I didn't catch that. So c squared equals a squared plus b squared. So 2 squared plus 5 squared, that's 4 plus 25, which is 29. So c is square root of 29. And so we have 0 plus or minus square root of 29. If you've got your calculator, you can see that that's plus or minus 5.4. Remember, we don't have to be exact when we graph the foci. Just if you recognize, and you need to recognize, that square root of 29 is between square root of 25 and square root of 36. So it's between 5 and 6. So as long as your foci are between 5 and 6 units away, you're good to go. So the asymptotes are at y equals plus or minus a over bx. So y equals plus or minus 2 over 5x. All right, now we're going to draw the hyperbola. First, draw a rectangle centered at the origin that is 4 units high and 10 units wide. The asymptotes pass through the corners. Now, I think it's easiest to go ahead and put the center on there and put your 2 vertices. So 0, 2, 0, negative 2. And then from there, so now you've got the height of this hyperbola, this rectangle established, okay? It is 2 units plus 2 units, the 4 units high. Now, from there, count over 5 units wide, and then go back down 2 units, and then down 2 units. Now, come back over to this vertex and go over 5 units, and there's another corner point. Then go down go down 2 units and down 2 units, and then the last thing you have to do then is to finish out this little rectangle. And you just dash it all in there. To draw your asymptotes, then you just go through the corner points and the center. Easy peasy to do. Okay, the asymptotes pass through opposite corners of the rectangle, just like I was saying. And then what you do is you start your hyperbola here at a vertex. You go up and over, getting closer and closer to those asymptotes. Then you drop down here to the lower vertex and you do the same thing. And then we typically go ahead and put the foci on. Now remember, the way I prefer to do it is instead of labeling the coordinates for the vertex, each vertex in the foci, I tend to put a V for each vertex and then an F for each foci. And you don't have to label the negative 5050 at all. All right, for example 2, we're going to write an equation of the hyperbola with foci at negative 40 and 40 and vertices at negative 30, 30. All right, since the foci indicate a horizontal movement from the center, and so do the vertices, we know that this is going to be a horizontal hyperbola with a horizontal transverse axis. So let's read what the solution says here. I bet it's going to be in agreement with that. The foci and vertices lie on the x-axis, equidistant from the origin. That's just saying there was a horizontal displacement there on the x-axis. So the transverse axis is horizontal, just like we said, and the center is the origin. The foci are each 4 units from the center, so C equals 4. The vertices are 3 units from the center, so A equals 3. Okay, so you go ahead and you put where the vertices are, and there's the center. Okay, and you can go ahead and put the foci. So the way I would have this, I'd have an F here where they have negative 40, a V where they have negative 30, a V where they have 30, and an F where they have 40, because we already know what the points are. Now, we're not graphing this, but if we were from there, since they've got the graph on here, let's talk about how they graphed it. All right, your vertices, once you have them on there, already give us, in this case, the correct width of the rectangle. We've moved 2 units to either side, so we've got a transverse axis that, 3 units to either side, so we have a transverse axis that's 6 units long. Okay, so from there, what we do is we're going to move B units up and down. Okay, in a second, we're going to see that B equals square root of 7. In fact, let's go ahead and look at that. Because C squared equals A squared plus B squared, you can solve for B squared by subtracting A squared from both sides. So B squared is equal to C squared minus A squared. So when we find B squared, we get 4 squared minus 3 squared, which is 7. 16 minus 9 is 7. Because the transverse axis is horizontal, the standard form of the equation is as follows. Okay, we're going to substitute 3 for A, so 3 squared is going to be the denominator underneath x squared, because again, this is horizontal, minus y squared. B squared is 7, so y squared over 7 equals 1. So our final answer for the equation is x squared over 9 minus y squared over 7 equals 1. Let's go back and look at the graph though. If b squared is 7, then b is square root of 7. Now, square root of 7 is bigger than square root of 4 and smaller than square root of 9. Square root of 7 is then bigger than, more than 2, but less than 3. And so you can see that when we go up more than 2 units, but less than 3. So approximately, the square root of 7 units. And then go back to the vertex you start with and do the same thing. If you want to, you can go ahead and extend over to where it's parallel to the other vertex, and then just finish out your rectangle. Sketch in the asymptotes, and then it's really easy to draw the hyperbolas. Now, the branches of the hyperbola. Now, this problem didn't ask you to do that, so you don't have to do that for this problem, but I just wanted to go over graphing one where it's horizontal, and also where one of your values isn't a nice integer value. So here with b being square root of 7, it's kind of good to just talk through that, because if this is on a non-calculated part of the test, you've got to be able to estimate what square root of 7 would be. So you think of perfect squares. Okay, 4 and 9. Square root of 4 is 2. Square root of 9 is 3. Square root of 7 has to fall in between 2 and 3. And so you just put the point somewhere between 2 and 3. If it's not perfect, that's okay. All right, guys. That is it. Okay, so 2 big types of problems: being able to graph and then identify the vertices, the foci, and the asymptotes, and then being able to take some information, determine whether you have a horizontal or vertical hyperbola, and then coming up with the equation in standard form. That's it for today. Do the problem to try on your own and be ready to go over it in class. If you can't do the problem to try on your own, you need to either review the video and try again, or come in and see me. I'm there all the time, ready to help you out. So do the problem to try on your own, and I will see you in class soon. Thanks again to Larson and Holt McDougall for their help.